In this video, I'm going to talk about the history of relational database. The first database were born in the 1960s, and they look nothing like the relational database we've come to know and love. So back then, the main models were network-based and hierarchical. So you can think of data organized like a sprawling spiderweb network or a big family tree hierarchical. So the first network data model, this was first to be implemented commercially thanks to Charles Bachman and Homer Carley at GE in 1962. It was quite flexible and was perfect for handling many-to-many relationships. So one object could easily connect to several others. But there were not many rules in places. So making relationship was kind of free-for-all. Retrieving data meant navigating through a maze, and you really have to know the twists and turns by heart. A programmer who could traverse one database network might be completely lost in another. So think of a taxi driver. So it was like a taxi driver in a pre-GPS era. A New York cab driver might know every street in Manhattan. But if we ask them to drop off passengers in London, good luck. Then came the hierarchical model pioneered by IBM's Information Management System, IMS. And this was in 1968. So here, data was arranged in very neat trees. And this is great for handling one-to-many relationships and blazing fast when working with very structured data. But if you try to model many-to-many relationships, and things got messy very quickly. Leaves in a tree can't have multiple parents. So the structure had to be duplicated or reworked, and this led to very slow performance as the tree got deeper and deeper. So worse, duplicated data can fall out of synchronization, and these will cause data anomalies. This is jargon for error in the data world, and they often did fall into anomalies. So updating one record meant carefully updating every duplicate, or you risk turning the whole thing into a maintenance nightmare. So while these early models were groundbreaking at the time, they were also tightly coupled with specific applications. They're very hard to navigate, and they lacked any solid way to prevent data redundancy or inconsistency. So remember the taxi analogy? So without structure and standardization, each system was in its own confusing city map. So the breakthrough came in June of 1970s when E.F. Codd published a revolutionary paper titled A Relational Model of Data for Large Shared Data Banks. So Codd, who is a computer scientist with a strong math background and working at IBM Research Lab at the time, proposed a very elegant and theoretically sound model based on relational algebra, which is a branch of mathematics. So in academia, everybody was thrilled, but in industry, people were not sold. So Codd was a visionary, but he was not a builder. He had this wonderful idea, but someone else needed to bring it to life. People questioned how practical the relational database idea really was. So after all, no one had built it at all. Plus, there were worries about whether the hardware at the time could even handle the complexity of such a system. So remember, this was in early 1970s. So even IBM hesitated to support Codd's idea, not wanting to undercut the profits of its already successful hierarchical database systems, which is IMS. So adoption started very, very slow. But over time, the prototypes built in universities and research labs, they began to show that relational model could actually work. But it wasn't until the late 1970s and 1980s that relational database really took off, driven by several important factors. So there are a few key impacting factors. The first one is the development of SQL. At IBM in the early 1970s, Donald Clamberlin and Raymond Boyce created a SQL, structured query language. This language made it possible to retrieve data without writing complex application logic. It's like building a smooth road to reach a beautiful but remote landscape. Suddenly, more people can access and enjoy the landscape. SQL was so beautiful that in 1986, it was adopted as a standard language by ANSI, American National Standard Institute, and also ISO, which is International Organization for Standardization. So, decades later, SQL remains one of the most widely used database language in the world. The second factor is advance in hardware. At the time, hardware was improving and the cost dropped significantly, the memory increased, and machines just became much more powerful. This eliminated one of the major concerns about relational databases, whether they could perform efficiently. With better hardware and optimized database design, relational systems became more viable than ever. 3. The third factor is initial success of a few commercial relational databases. The third factor was the initial success of a few commercial relational databases. A few key players brought a relational database to the market. Matrix Relational Database Store in 1976 by Honeywell was the first commercial relational database. Unfortunately, it faded from the spotlight partially because it used a proprietary query language instead of SQL. Oracle, then named Software Development Laboratories, released version 2 in 1979, and Ingress, a research project started in 1973 at UC Berkeley by Michael Stonebraker and Eugene Wang. This was considered superior by many, but it was not commercialized until the early 1980s, and this lost ground to Oracle. And this also was partially because it did not use SQL. On a side note, Ingress is the basis for Microsoft SQL Server and Postgres, the largest open-source relational database system. IBM, ironically, was the slowest to commercialize Codd's idea. IBM launched DB2 in 1984, 14 years after its employee Codd's publication. So fortunately, DB2 eventually found success. So that's a lesson there. So just as today's AI companies open source their models to dominate the market and influence standards, SQL's openness gave it an edge. So the choice to embrace standards can define the winners and losers in tech. The first factor, which is a game changer, is data independence. So both the most important contribution to Codd's model was idea of data independence. This means the logical design of the data, how it is structured and related, should be independent and separated from how it is stored physically. So a database designed for Microsoft SQL Server can run on Oracle and vice versa. And this is because regardless of the internal implementation, they follow the same logic, structure, table, columns, and relational rules. So SQL is really the universal language to access data from any relational database. So data independence created a separation between logical design and physical implementation, which in turn liberated the innovation and rapid growth of relational database. To make this clear, let's use a real-life analogy. Imagine you run a small restaurant. At first, you do everything. You take the order, you cook, you serve, you handle the payments. Think of the kitchen as the database, and the customer orders as applications trying to access the data. Since you know everything, Things work well until your business really booms. Now you're overwhelmed. Now there are so many customers, so orders are delayed, mistakes happen, so you try to hire somebody to help you. But now both you and your new staff member are trying to do it all. So you try to cook and serve and handle payment, but it's chaotic. Everyone needs to know all the recipes and all the orders. If you make any changes like adding a new item to the menu or changing the kitchen layout, now this will really throw everything off. The system doesn't scale well. So now you decide to separate the kitchen duties from the rest. You implement a proper menu, and this menu is like the logical design of the database. Now the waiters only need to know what dishes are available, not how they're made. You, the chef, just need the order slip. You don't need to talk to the customers. If you change the stove or reorganize the pantry, you're changing the physical storage of the data. But the menu doesn't change. If you add a new dish, it can easily be added to the menu, and the waiter can offer it right away to the customers. So this is a concept of data independence. The kitchen here is a physical storage, and the waiter applications are connected by the menu, which is a logical schema. So the change in one does not really break the other one. So everything runs smoother and faster and more reliably. So now let's sum up why relational database became and still are the cornerstone of data management. So virtually every mid and large size organizations relies on relational database for good reasons. The first reason, tables just make sense. Data in relational databases are organized into tables with rows and columns. This is very clear and logical and intuitive. Human beings have been using tables for many, many years, and this familiar structure just makes data so easy to understand and easy to manage and query. The second reason is that relationships can really prevent data redundancy. So one of the superpower of relational database is their ability to define relationship between two different data objects. This will allow us to have rich connections across information, and this will prevent data duplication and power meaningful analysis. The third reason is easy data access with SQL or SQL. So SQL really makes retrieving information very easy and intuitive and simple. Last but not least, the ACID property. ACID stands for atomicity, consistency, isolation, and durability. ACID property means reliable transactions. Relational databases guarantee data integrity and reliability through something called ACID. The first one, atomicity. Atomicity means that a database transaction either happens entirely and successfully or not at all. It cannot get halfway through and stop like an atom. It cannot be broken down mid-process. So let's look at an example. Imagine you have two bank accounts, account 1 and account 2, each with a balance of $500. You request to transfer $100 from one account to the second account. So this transaction involves two steps. First, we need to withdraw $100 from account number 1. Second, we need to deposit $100 into account number 2. So if both steps complete successfully, we will see $400 as a remaining balance in account 1, and then $600 as a balance in account number 2. So the total account remains unchanged at $1,000. But what happens if something goes wrong in the middle of the transaction? Suppose this $100 is already withdrawn from account number 1, but now an error prevents it from being deposited into account number 2. So now the system only shows a total of $900. So that's $100 missing. On the other side, if the deposit into account number 2 succeeded, but the withdrawal from account number 1 failed, you end up with 1,100, 100 surplus that should not exist. So that's where atomicity comes in. It ensures that all steps of the transaction succeed or none of them do. If one step fails, all changes already made are rolled back, returning to the system to its original state, which is $500 in each account. Sure, it's not ideal when a user transaction is rejected, but it's far better than losing $100 or accidentally duplicating funds. So in a system that manages money, maintaining that data integrity and trust is very, very important. Consistency. This means the database always follows some rules. So for example, your bank will never let your account go below 0. That is a constraint the system reinforces. This makes sure that only the valid transactions can go through successfully. The third one is isolation. So when multiple transactions can happen at the same time, each one will behave as if it's the only one using the database. If you are transferring money while an automatic bill payment kicks in, so what should the database do in this situation? Or if an automatic payment is triggered while a withdrawal is still being processed, should the account balance be based on $500 or $400, which is the amount after the withdrawal completes? And what should the balance be after each transaction completes? So that's where isolation comes in. Isolation ensures that the database handles each transaction separately, even if they happen at the same time. So behind the scene, the system queues and processes them in a way that avoids overlap. So no transaction can interfere with another. So think of this like the database opens a dedicated traffic lane for each transaction. The cars may enter the intersection at the same time, but they are routed so they never crash. The system keeps both the transaction consistent, even though they can happen concurrently. Durability means that once a transaction is confirmed, it's permanent. Even if the system crashes, the data is safe because of the logs and also data replication. So when a data change request is made, the first thing the database does is record it in the transaction log. And this is a crucial component that tracks every action. Only after this is confirmed and a confirmation sent to the user, and now finally the actual data is written to the main data file. In addition, a database can be regularly backed up on a scheduled basis. If something goes wrong, like a crash or data corruption, the data can be restored using both the backups and the transaction logs. So together, they really help us ensure that no changes are lost and that the system can recover reliably. The last one is scalability, but scalability has a limit. Relational database can scale, just add more memories, CPUs, or big servers. However, this scalability worked best before the explosion of big data. Even now, with so many different types of databases to choose from, relational database remain the dominant force for most organizations. And this is especially true for core transactional and analytical systems. They continue to be the workhorse for structured data, complex queries, and applications that demand very strong data consistency and integrity. It is safe to say that well over 8% of the organizations still rely on relational database in some capacity. So if you take a look at the table, this shows top 10 most popular database engines as of 2025. You can see that 7 out of 10 are still primarily relational, and only 3 of them are NoSQL databases. Of course, most major relational database vendors now offer multi-model support. This means that their platforms can handle more than just relational data. But make no mistake, the dominance of relational model remains clear and unquestionable. Alright, so in conclusion, in this video, we explored the history of relational database systems. We also explained the key factors that really sparkled the creation and fueled the widespread adoption of relational databases. We introduced the pioneering individuals and organizations that plays very important roles in this process. We also explained the core principles behind the success of relational databases and why they become the backbone of modern data management. So finally, we highlight their continued relevance. More than 50 years after E.F. Codd published his groundbreaking idea, relational database still holds a very important position in the data ecosystem. Thank you for watching this video.